Good morning to all. This is Anvesh. Today my topic is about 3 and data structures, algorithms, and data structures for new models of computations. So, about the in earlier days of computer science, the community settled on a simple standard model of computing on a basis of canon of general purpose algorithms and data structures. The standard model of computing has a one processor that performs a single instructions at a time, copies memories that is in uniformly accessible with negligible latency, readily available, uh, readily available precedent storage with significant latency, input and output that is insensitive to content or context and orders of magnitude slower, resources and connections that do not change, and no significant corners about energy used for component failure, permanent or intermittent. The canon of data structures and algorithms include list, quick sorts, and Boehm 1, string search trees, and hash tables. Kunz even began what was intended to be a complete encyclopedia of computing, although new and better. Short routines are regularly sent to editors of dictionary of algorithms and data structures. None has been both new widely applicable. The most recent general purpose data structures is a skip list which was invented 1989. Work continues in specialized areas such as graphics, distributed systems, user interaction, cyber physical systems, and artificial intelligence, except perhaps for quantum computing algorithms. General textbooks have background. Few actual computers match the standard model in all aspects, although hardware catching and system support will approximate the standard model. Developers must be aware of constraints and of the software execution environment, new constraints of time, space, energy, and hardware motivation, new of thinking, and lead programmers to need new approaches to old programs. So many advances has been made in hardware and systems salvage staying within the standard model forgets much performance editing advantages that are available to exploit in the heterogeneous multiprocessor flash memory, energy aware computing, cache, and other anti-sport computing with graphic co-processor networks of many simple devices and streaming environment in some anonymous ways in maintaining or staying within the standard computing model. In the other cases, additional squanderedly if we use without read to their particular strength and weaknesses. Now, for example, flash memory is used in solid state drive, a memory card for cameras and smartphones, where out individual bits in flash memory can be set, but bits can only be cleared for erasing an entire block of memory. Block of memory can only be erased up to 100,000 times before excessive errors occur. The entire block of memory that then became unaccessible to extend their usable life. Many flash memory subsystems use sophisticated algorithm to spread writes throughout the memory and still maintaining the abstraction of pre-sentence memory that is insensitive to to write location This is often accomplished through generalizing file system or log structures file system whose pattern or writes match flash's memories well. Additional efficiencies may be available to the software developer by using data structures specialized to flash memory, such as taking device characteristics into consideration can improve solid state disk responsive by 44%. Similar constraints and opportunities arises because of multi-core machines in which there is a parallelism on every desktop, distributed computing in which one can use hundreds of machines only for 1 million seconds, and cloud computing in which extra processing is always available for a price with some delay to request and provision additional resources in additional micro power and ubiquitous sensor are best used by applications that are treated input as stream of values to be processed instead of a static set of data. Power and thermal aware computing is a growing stream of values to be processed instead of a static set of data. Power and thermal aware computing is growing important in mobile devices and huge server installations. Today we accept computing system distributed across the entire earth to function as well as signal coherent whole in spite of speed of light delays, which often requires carefully catching. Examples of algorithms and data structures. In the section we give for four instances of elegant generally used algorithms and data structures that were developed for particular circumstance but are not widely known. They are listed the opportunities to create new algorithms of data structures motivated by the new computing constraints. Reservoir sampling. For the first algorithm, consider a stream environment, that is, items arrive one at a time. The program does not know how many items will arrive, or equivalently an answer may be required after an unspecific number of items have arrived. So since we don't know how many times there will be, we limit resources to be a constrained amount of memory plus a counter that requires log and bits. As a real world example, imagine the network of tiny sensors deleting pollution randomly. A sample is requested from every sensor in the network, the tiny one of the item randomly, with all item having equal chances of being chosen. If the number of items is known beforehand, one could generate a random number in the range of number of items. Alternatively, one can store all items possibly in some data structures that can grow as needed and choose one when need. Neither of these standard solutions satisfy constraints of not knowing the number of items beforehand. A simple solution is attributed to ln g. It is requires storing the items chosen so far, a counter that holds the number of items that from the stream so far. The begin store the first item and the set of n to l for each new item replaces the chosen item by by the new item, which probabilities 1 by n plus 1 and increment n. The proof algorithm correctness is simple too. Clearly we end up with the one item, but does every item has an equal chances of being chosen? We sketch an induction proof. The first item is kept as a chosen item being chosen after the second step. The first For the first induction step, uh, assume that every one of n item has an equal previously chosen item and therefore retain with a probability of n by n plus 1. Multiplying with we find that each of the being kept on n by n plus 1 into 1 by n is equal to 1 by n plus 1. So every one of the n plus 1 item has an equal outside of stream processing environment. So why should this algorithm be used? Typically everything in memory, and the program can do two passes. The first pass counts the number of items and the second pass chooses a number of randoms. So suppose selections is computationally intensive. For example, only number of prime numbers or candidates to be chosen randomly if would be insufficient to check primarily in the first pass of count the choose a random number k, then repeat the primarity checking when counting to the find the kth and the kth item. A program might catch the primes identified in the first pass, but then program is more complicated. As several authors have pointed out, reservoir sampling can be easily extend to pick m items at random for a stream. The insight is to keep a new item n plus 1 with the probability of m by m n plus 1. If we decided to keep a new item randomly, choose one of m item to replace. This can use to efficiently choose a random sample from a database. Typically, one selects all candidates from a database, then choosing a random sample. The next algorithm we consider also takes place in stream environment. Suppose items occur multiple times, and one of item is known to occur more than half the item. As a real world example, consider an HOC set of paths of their items around the ring. Non-sensor, what the algorithm could and single sensor used to identify the majority items in the stream. Storage is need for two things: a tentative majority item and unmatched count. Note the tentative majority item to be arriving items and set the count to 1. If the count is positive, then the majority item increment the count. If the count is positive, the arriving item does not match, and the tentative majority item is majority item if one exists. If no item occurs, majority of items in and any item might be tentative item at the end of and then there is no guarantee that the item will be plurality with will be kept. Compacting an array, finally we present a parallel algorithm with the multi-core machines being the normal for persons. Cloud distribution computing makes the new every more urgent. The problem was the problem we the problem we consider is compacting an array, that is copy all non-zero entires from one array to another array. A simple serial algorithm can accomplish this faster using parallel processing with a minimum of complaints. To compact an array, assuming theta n hardware and using a fewer entires in cache and page tables. Other variants such as a cache observability algorithm, simplex k way heaps, min max heaps, and van Edeme boss layouts similarly work for better with actual virtual memories. WordSpam creates one thread for each index. Each threads run its own copy of the code in the body of spam. Each intermediate thread passes the destination it receives from above to its left subtree. Thus, every value of from A is put to in unique place in B. Each despite value in unique since the least value in right subtree is give beyond the highest value in the left subtree. Although compact an array is not common prefix, some is used in sorting. Give several other commonly used algorithms with a easily parallelized similarly. New constraints and opportunities in computing such as highly parallel, cloud and energy aware computation can lead the novel, elegant, broadly applicable algorithms and data structures. We call for renewed interest and in resources for research of basic algorithm and data structures. Campy says programs should be taught some catch aware data structures and algorithms to understand the benefits of and need the such improvements more to point 6 IT professionals diagram of threats to compute the prefix sum operations. Such data structures and algorithms must be as an convenable available from standard libraries as standable model algorithms currently are. Busy professionals seldom invest extra time or effort to obtain the best tool for a job. Inadequate tool is already at hand. Acknowledgement the certain commercial entire equipment or materials may be identified in this document in this order to describe an experimental procedure or concept endorsement by the National Institute of Standards of and Technology, nor is best available for the purpose. This document was written in the National Institute Standards code. This is not just copyright protection in its public domain. So thank you.